What I'll be talking about is a problem that I've been struggling with for a while, and I'll be asking for help on it. If anybody has any ideas, I've been considering, actually, I'm getting frustrated enough with the problem that I'm considering monetary rewards for people who make a significant contribution. And although I haven't established what a good monetary reward might be for this problem, if somebody does have an idea, we can negotiate that aspect by email or something. Okay. Anyway, I will be talking about an integer problem, and by its nature, integer problems can be difficult and not very easily analyzed, and that's what I think is happening in our case. Here's the integer problem, and I'll be just giving it in its mathematical form and then describing in some detail later where it arises. Suppose you start with a k-dimensional vector u, and suppose that the entries of u are chosen randomly as plus or minus 1. So that's those are integers, and with equal likelihood of being plus 1 as minus 1. And let H be a k by k matrix composed of independent complex Gaussian random variables, zero mean and unit variance. I'm going to define a gamma, a norm, where I take H, invert it, and multiply it by u, but I'm going to add to u integers multiples of 4, basically. And what I'm going to ask is to minimize this norm, u plus 4L times H inverse, and I'm allowing the L's to be taken over all possible integers, going to plus or minus infinity. And because I'm going to be thinking about complex problems here, I'm actually going to let u be a complex quantity where its real and imaginary part are plus or minus 1. And so therefore I'm going to allow L to also have real and imaginary components to it as well. And so I'm basically taking u and to its real part adding multiples of 4, and to its imaginary part also allowing multiples of 4 to be added. And I want this minimized, this norm. And you see, by adding multiples of 4, I'm avoiding 0. I'm not letting u, or the sum u plus 4L, take on the value 0, because it would be a trivial solution to have that vector u plus 4L equal to 0, which would be the minimum. So since I'm avoiding 0, I'm asking what is this gamma and how is it behaving as a function of the dimension? How, what does it say its expected value? Since the h is random, the u's are random, is there anything we could say about gamma in general? And specifically, how about for large k? So in particular, I'm interested in expected value of gamma. I'm interested in gamma's distribution. It seems to be, and I'll show you in the slides that follow, that gamma will approach a delta function as k goes to infinity. It'll be centered at a particular point, which will be, of course, its average. And we'd like to understand what that point is, what its average is.
So why does it have to be 4? Is 2 not good enough?
Yeah, that's what I'm thinking.
Well, okay, so what I would like to do, what I would really like to do is, you'll see why 4 plays a role in this later on. I could have done something like 2 and avoided 0 also, but what will end up happening is I want the original 2 values of u are plus or minus 1, and I want the resulting values to be spaced far enough away from the original values, and 2 would not allow that. 2 would allow minus 1, for example, to be mapped onto plus 1, and I want to avoid that possibility. You'll see why later on. But right now, minus 1 can only be mapped to 3. If I see 3, u plus 4L, if any value is 3, I know that the original value of u was minus 1 because there's no other way for me to get to 3. If I had allowed 4 to be 2, then there would have been these minus 1s and plus 1s could have overlapped one another after being multiple of 2 is added. And you'll see why that's important later. It's not important in this problem. So here's some tantalizing little tidbits. gamma as a function of the dimension k. So on the x-axis here I have dimension. On the y-axis I have values of gamma after having done some tens of thousands of simulations, and this is purely by simulation. And you'll see gamma in this blue curve here starts off at a relatively high value, but seems to be approaching some sort of limit as k goes to infinity. And I put in red dashed lines to indicate a limit, but I don't know what that value is. I just kind of do that by eye. The magenta curve is the fraction of the L values. Remember, the L on the previous slide were the integer multiples here, the L values, that end up being non-zero when I do this minimization. So roughly 20% of the L values end up being non-zero in that minimization. So 80% of them stay zero. And it seems to be starting off, of course, small and then hitting also some kind of a limit. And any kind of waviness in the limit is because I haven't done enough simulations to flatten it out. Okay, it looks intriguing. How about the density? Well, two values for k here. The blue curve represents dimension 5. The red curve represents dimension 10. And the dashed line represents the averages, the means of those distributions. But you're seeing on the x-axis gamma versus its PDF. And this again is simulated.
Convergence to a delta function, is that something you observe through simulation,
Yep.
or do you establish it?
No, I can't establish it. I'd love to be able to. And in fact, as k increases, the means seem to decrease. As you saw in the previous curve, how gamma behaves as a function of k, you're seeing it here. The means seem to decrease to some limit, and the density gets narrower and narrower and narrower. That's just an empirical observation.
Do you think the fact that the number of non-zero entries is going to 0.2 and that the limit looks like it's going something like 5 is related?
I'm not sure. Really don't know. I know very little about this problem. I'll have a little more definite things to say later, and maybe the 20% business will reappear. So what is the source of this problem? Well, here's a little bit on the wireless side of things. So till now it's been just purely mathematical or integer problems. The source of the problem is a precoding problem in wireless, and the idea is that if you were able to get channel information at a base station and you had some antennas available to you, you could use this channel information and those antennas to broadcast to many users simultaneously. And the broadcasting is done by a precoding trick. And the precoding trick involves the minimization you saw, the integer minimization. So the assumptions I'll be making, at least for the wireless side, so I'm going to switch a little bit into a wireless mode, is that we have a base station, we have antennas, we have a channel information, we have multiple users. These users are only having one antenna themselves. So this is the scenario where we believe that things are evolving a bit more, that users, the terminals, will not be burdened with antennas, and that only a base station might be. But yet, we're going to get incredible gains by having these antennas because we have the channel information at the transmitter, and this channel information will be used in a precoding step. So the trick we're going to use is precoding. We like to call it sphere-encoded multiple messaging. The reason being that the minimization that I showed you, this minimization is done by an algorithm called the sphere decoder, and in our case we're calling it the sphere encoder. Because it's an integer algorithm, it's a non-trivial minimization, and so some special tricks to make it fast need to be done. I won't be going into any of the details of how we do this minimization. I'm going to leave that to either questions if people are interested, or I won't mention it at all. Oops, going the wrong way. So again, wearing my wireless hat, the old multi-antenna paradigm, and old is really relatively speaking, that the idea that if you added antennas at a base station and you gave everybody else antennas, and here I've just, as an optimist, put 10 antennas on both the base station and on these users, the idea being that you add antennas everywhere and you get 10 times as much throughput as if you had just one antenna everywhere. And that's sort of the rule of thumb people were running by, because in a point-to-point scenario, if you do add 10 antennas to either side of a link, that link gets 10 times better. It stands to reason that in a network scenario, if everybody has 10 antennas, then the whole system as a network will run 10 times better. And we now know that's probably an exaggeration for several reasons. First and foremost, we can't really hope for terminals to carry 10 antennas. And so if we really believe that we want 10 times the throughput that we had before, we're going to have to try something else. And, well, this is, of course, just a review here for people who have looked at the problems of antennas in MIMO. In a point-to-point scenario where each user is receiving a vector through antennas, and they each have a channel H with some data X that was transmitted, then the capacity to each user is just given by this formula here. And we'll review that in great detail. But this capacity, if you evaluate it, is roughly 10 times larger than the capacity of a single antenna link. And the idea is that if you had many users, you're going to use some kind of multiple access, like CDMA, TDMA, to access all these users in the same fashion as you would have if you had one antenna. All right? That's the old paradigm, and it's really seeing only limited success because of the various problems related to the terminals. In a new paradigm, we're just going to allow the base station to have 10 antennas, and the terminals are just going to have one. And in this case, fundamentally differently than before, which I did mention, the H's are known to the receivers. Now we're going to assume that the channel between the base station and all these individual users is known to the transmitter. Okay, so this is a little bit of an extra burden for sure. But the burden of having antennas at the users is eliminated. And if you look at the capacity formula, you'll see the capacity of the scenario where the base station has the antennas and the channel information. It has a very similar form to what you saw on the previous slide. And if you evaluate it, it's roughly 10 times what it would be for one antenna at the base station. And this is a true network phenomenon. It's called the sum capacity. It's the capacity to all the users summed up will be roughly 10 times better if just by adding antennas at the base station. And so this seems like a viable paradigm for having a network really benefit from the use of antennas. And some of the details here, because since I will be concentrating on this scenario, we see that because each terminal has only one antenna, the channel between the base station and the terminals is given by a vector, and here I've written them as H1 through H4. And if we stack all these vectors into a matrix, then that's given by this matrix H. And what's received at the various users, I can lump that into a vector Y, and that's related through what's transmitted X through this matrix H. Of course, the Y, each user sees only one component of this Y. This Y vector is not being received at one place. It's being received by many terminals in many different places. Any questions so far? Am I going too fast? Too slow? All right. So now, looking at the capacity, that capacity formula that I showed you on the previous slide, I'm just going to pick an operating point, and we'll dwell a little bit on that operating point. 11.2 dB is the noise variance at the terminals. Rho is given as 1 over the noise variance. And the blue curve represents 4 antennas talking to 4 users, and the red curve represents 10 antennas talking to 10 users. This is just purely the capacity formula. And just re-emphasizing the linear growth, the red curve is 2.5 times better than the blue curve, because the red curve has 2.5 times more antennas than the blue curve. So in this particular scenario, every user is getting 3 bits, And we're servicing 4 users with 4 antennas in this scenario for a total of 12 bits. And we're servicing 10 users in this scenario for a total of 3 bits. And no added transmitted power, just more antennas. Okay. So it's a pretty compelling curve. So the new paradigm has some big pluses, some of which I've already mentioned. The terminals can be dumb. They can have one antenna. They don't need to do fancy processing. They don't need to have complicated RF or large, bulky antennas hanging out of them. The paradigm is very good on the downlink. Here I'm talking about the base station talking to the users. That's where we often think that it could be more data intensive than the uplink, and so we need help on the downlink very often. One really nice feature is that the scattering environment doesn't really have to be rich for this tenfold phenomenon to work. Unlike the point-to-point case where if I'm talking to a user through multiple antennas, the requirement for the tenfold gain is that my path between who I'm talking to and myself has to be very, very rich. In this scenario where we have the users in separate locations, most typically the environment does not have to be rich. It's just that the users have to be uniquely identifiable. So a line of sight environment will work fine as long as the users are not on top of one another. A rich scattering environment will work fine as well. Right? And this is reflected in the H matrix because the H matrix is composed of many users into one, whereas in the point-to-point case, the H matrix is composed of just one user at a time. Right? So we think this is a really nice feature. There's a negative though. The base station needs to know the channel, and there's some effort, of course, involved in that, which I won't go into here. So, getting a little bit back to the gamma problem, you're seeing gamma appear again. Again, we transmit a vector X, it goes through a matrix H, it's received by many receivers in a vector Y. Each receiver has one component of that vector, and there's additive noise, of course. So you can try to imagine ways to send separate messages to the receivers. Now remember, the receivers can't collaborate to decode their components of the signal, the intended signal at their terminal. So we need to come up with a transmission scheme that allows them to decode each of their data separately. One thing you could do is just invert at the transmitter. We know H, why not just precode by multiplying by the inverse of H at the transmitter. So we're sort of pre-scrambling the signal, or pre-unscrambling the signal if you like, because the channel matrix H is going to then undo what we just did and give us, in this case, when we just use the inversion, a direct line between the transmitter and the individual user. So what's received, Y, is related to what's transmitted as data, U. Sorry, I skipped a step. I'm going to let X be what's actually sent out on the base station's antennas, and U actually be what's desired signal at the receiver. So U is really what the receiver wants to decode. So this in front here represents the precoding, so to speak. Okay? So I'm going to precode the data U with this and transmit X, and what's received then at each receiver is Y1 is going to be U1 plus W1, Y2 is going to be U2 plus W2. So that's a really ideal scenario where everyone can decode their own message separately. The big trouble is that nasty gamma. In the case where I use channel inverse, the gamma plays the role of a normalizing constant. I have to limit my transmit power, and in my case, I'm just going to assume that I have unit transmit power. And the gamma then is going to play the role of normalizing this to unit energy. And what happens is gamma, in the case of channel inverse, is huge. And so therefore, although this looks like an ideal receiver equation, gamma being as big as it is going to take the desired signal and pull it down into the noise, and then decoding will be difficult. And I'll have more to say about that. So in an attempt to improve this, we might try, and the reason gamma is so bad is because inverting the channel is generally a tricky thing. If the channel is ill-conditioned, the matrix H is not well behaved, and putting an inverse on it can often, it just explodes the power, explodes the entries of H. So gamma is ill behaved because H is ill conditioned. So we can try to fix that by making H better conditioned before we invert it. And one way to do that is just to add a diagonal loading term. Yeah.
Is it that your criterion is sum rate?
Sum rate.
So if M is the number of transmitting antennas and K is the number of users, so can't you make the number of users smaller and avoid that problem?
Right, but then I'll be far from capacity because the sum rate, to get as close as I can to the capacity, if I had M antennas available to me, to get as close as I could to the sum capacity, I would need to serve as many users as I have antennas. Any smaller number of users would make this behave better, but would cut my capacity that I'm getting because it's a degree of freedom lost for every user that I cut out. So if I served half as many users as I had in antennas, for example, I would get roughly half the total capacity I could have gotten if I had serviced all users. I mean, I'm just speaking ballpark. So I'm really trying to achieve the full capacity of all the antennas available to me. And the only way really to do that is to service as many users as I have antennas. In fact, if you look at the capacity calculations, you really should be servicing more users than you have antennas to get really the full capacity. At least that's what the formula seems to indicate. But we're going to stick to the same number of users because that's where we get the biggest bang for the buck, so to speak. So we could try to fix the inverse with diagonal loading. And of course, the bigger we make alpha here, the better behaved the inverse is. And so, of course, that doesn't come for free either because what happens is if I add alpha, I make the inverse well behaved, but then when I multiply, the channel multiplies by H, it's not going to cancel so well anymore. And what I end up getting at the users is their own data, but a lot of interference from other users lumped into this W prime here. So making alpha bigger will help my inversion and help gamma, but adds junk into the interference here. So that'll have some role, but it won't be the dominating role in what I'm talking about. In the end, we're going to actually use that, but we're going to more importantly use an offset to the data itself. And what happens is that we're going to take the data that we transmitted and realize that it represents a vector. It's being pre-multiplied by the inverse of the channel, and we'd like this data to not explode when we multiply it by the pre-inverse of the channel. It's not inverting the channel itself that's causing the problem, it's inverting the channel times the data. So is there a way to take the original data and try to steer it into a low eigenvalue space of the channel? And that's what we're going to try to accomplish by adding offsets to it. So we're going to take the original data vector, which is random, and try to steer it into a good place. And the way we'll do that is to prearrange some integer offset, and that's the tau, which played the role of the 4 early on, the first slide. We're going to choose an integer offset multiple of tau to add to U, and each terminal is then going to use a modulo arithmetic to remove that integer offset at its terminal and get back to the original data U. And this is kind of connected with your question about why we couldn't use 2 instead of 4. The terminal has to be able to remove the effect of the integer offset. If I had used 2 instead of 4, I wouldn't be able to do that because the same plus or minus 1 might either one might have been mapped into the same integer if I had used multiples of 2 instead of 4. And so getting rid of the integer multiple of tau wouldn't have been possible then. Is that fairly clear?
Yeah, but how come then is it clear that like tau can't be 3.5 or whatever?
Yeah, no, that's not clear. We actually don't know what the best value of tau is. We just picked 4 as an example. Yeah. So here's like a block diagram summary just to put it all in kind of one picture. We're going to have coded message symbols U1 through UK intended for the K receivers. We're going to be using a precoding. This is a linear part of what we're doing. We're precoding by this channel here. we're going to get a vector S, but we're going to add an integer offset using a quadratic integer optimization. So what we're transmitting then is H. This is just a very kind of symbolic way of a symbolic thing of what we're doing. So to the U, we're going to be adding an integer offset, multiplying by this precoding matrix, normalizing, and then sending over the antennas that we have available. The terminals, the receivers, are going to be modding out the integer offset, and then after that, they're just doing everything as they would have before. Just decoding using soft decoders, etc. Is that clear? So here's a measure of how well this performs. Just skipping ahead as a prelude to performance, and I'll come back again to this slide when I've talked a little more about the algorithm. So what do we have here? We have two red curves and two blue curves. So the pink line here represents the capacity line that I showed you on a slide some time ago, showing the operating point, 11.2 dB. This red curve represents using the diagonal loading but not the integer offset. This is the kind of performance we can expect for 4 antennas and for 10 antennas, for 10 users. So that's using just diagonal loading. If we use both the diagonal loading and the offset, we move closer to the capacity line. And oddly enough, the 4 antenna works, again, worse than the 10 antenna case here. And as another phenomenon that we observe, the larger the dimension and the more users you service, the closer you actually get to capacity. So, and this we believe is related to gamma. We think gamma, which is our normalizing constant, is getting better and better behaved and shrinking as our dimension grows. And so there'll be a limit how close this gets based on dimension, and that limit is determined by gamma. So
this capacity curve you drew is per antenna?
You mean this right here?
Yeah.
That is the operating point, 11.2 dB that I showed.
This sum, yeah.
That let me just get back to that here. That's this point right here. So this capacity curve says that at 11.2 dB, I could have, for 4 users, attained 12 bits, 3 bits per user, basically.
Yeah.
And at 10 users, attain 30 bits. So that's the line that I drew there. And I'm trying to get 3 bits. In this curve, I am trying to get 3 bits because I'm skipping a lot of details. I'm using 16 QAM symbols with a rate 3/4 turbo code. So that's 3 bits per user. And this is how far away we are. Now we think 4 dB is pretty close. I mean, in Gaussian terms, 4 dB is not close to capacity. People are talking fractions of, they're in the hundredth or thousandth decimal place now, I think, when it comes to capacity for a Gaussian channel. But here we're talking about servicing 10 people simultaneously, and the game is a completely different game here. When we're trying to service many users, closeness to capacity is a much different game. So getting back to the gamma, this is our normalizing constant. So this you saw a few slides ago. Suppose I'm actually going backwards in time now. Suppose we just do channel inversion and just try to understand how.
Sorry, I have a question on your previous.
Yeah.
So when you do the 16 QAM with whatever rate, so how are you treating the interference here now? So?
I'm sorry, by what? By the
I sort of understood when you sort of do the sum capacity formula.
Right.
So now I'm saying, you're saying that you're using some kind of a modulation with a turbo code. So there are multiple transmissions from this, whatever, 4 antennas, 10 antennas, whatever you have at the base station.
That's right.
So all these single antenna mobiles.
Yep.
So the only thing you're doing is basically having this precoding.
Right. And the integer offset.
And the integer offset.
Right.
And when the mobiles decode, so
all they do.
What is it that they need to?
All they do is do a modulo of the integer offset and then decode. They don't do anything else. They don't need to know anything. They don't need to know about the existence or what the other terminals are doing.
I think you have one more question.
Oh.
Now, Bert, you're not, you want to do something simpler than dirty paper coding, is that right?
I didn't say the word dirty paper.
Okay.
That's a dirty word, I think. But
why is it that in the mix as part of the
Actually,
possibility?
right. So, if you do that, you would get very close to that line, I think.
That's what I was saying.
Yeah, because Dragan did this in his, one of the things he did in his thesis.
so, right. This capacity formula that I showed this one. This capacity formula is actually a formula that really relies on dirty paper for its existence. So, to achieve it, in theory, dirty paper types of tricks could achieve it. We think we can achieve it or get very close to it without doing any of those dirty paper types of tricks.
That was my question.
That's right.
You're doing something that's simpler.
Right. That's right. That's right. So we're doing, in some sense, we're doing a vector problem where the dirty paper problem, even for a scalar case, seems to be relatively unsolved. Solving it now for a 10-user type of vector case, which is what that capacity formula would require, would, I think, be 10 times worse unsolved in some sense than the single, 10 times more unsolved than the other case. Gamma is at the heart of how well this behaves, this technique behaves. And so it pays to look quickly at how gamma behaves itself. And getting back to just using pure channel inversion, we can see why that performs so poorly. So pure channel inversion is just this. It's generalized here to be the pseudo-inverse in case you had more antennas than you had users, but we'll be generally using just a square case, and so this is just purely the inverse. And gamma is our normalizing constant. So again, repeating myself, the channel multiplies by h, and then the terminals then receive this. And the reason why that looks good but is bad is because gamma is poorly behaved, and you'll see that soon. So how do we choose gamma? Well, gamma, if S is our unnormalized signal, then gamma can be chosen to be the expected value of this S, or just the instantaneous norm of this S. And that way we get a normalized quantity that's 1. And we generally choose this quantity here, but we could go with either one. The performance ends up being the same. And if you choose the gamma this way, you can do the analysis and show that the sum rate to all the users as normalized by the number of antennas, that limit, is given by this formula here, where beta is the ratio of antennas to users. And in the very specific case that we're interested in, where you're servicing as many antennas as you have users, that's where beta equals 1. You'll see that this is 0. So it's suggesting that we're getting a 0 units in linear growth per user, well, in the square case where m is equal to k. And that seems like a bad thing. Although, as Jerry, as you pointed out here, if this ratio beta is anything other than 1, we can get some linear. So let's look at gamma a little more carefully when beta is equal to 1. It turns out we can compute the density of gamma. And if you look at this density here, gamma, and the real source of the problem here is that gamma has infinite mean. So therefore, defining gamma to be the expected norm of what we're transmitting, it seems to have infinite mean, and so that's a horrible situation. And what's the source of the bad mean on gamma? Well, it's the eigenvalues of the matrix H. And in particular, the largest eigenvalue of the H inverse also has infinite mean. It has its density here and infinite mean. And gamma, of course, is just going to be a weighted sum of these eigenvalues, because I'm multiplying the data that I'm transmitting by H inverse. And so with some chance, I'm going to be landing on the bad eigenvalue of H, and that's what's contributing to the infinite mean for gamma. So here's representing the weighting of the eigenvalues in the inner product of U and the eigenvectors of H. So we can look at the sum rate for channel inversion, the capacity for channel inversion. The blue curve represents the actual channel capacity for a given operating point, 10 dB, as a function of the dimension. So that's growing linearly, and that's what we'd expect. But this curve here represents the sum rate for channel inversion itself. And you see the gap between channel inversion and the actual sum capacity is enormous and getting bigger as K grows. In fact, the sum capacity, because gamma has an infinite mean, is hitting a limit. And we can explicitly compute that limit. So anyway, I've sort of been beating this channel inversion as being horrible, which it is in its raw form, but we're going to try to fix it. So how can we make gamma smaller? Two possible methods. One is, as I mentioned before, try to add some regularization to the inverse and hope that the eigenvalues of this whole thing are a little better behaved than the eigenvalues of H alone. The other thing that we're going to do is to perturb the vector u. We're going to take the u and add an integer offset to it, so that the sum that we get from adding the integer offset does not lie along the large eigenvalues of this inverse. And those two tricks together are going to combine to give us a very small gamma. So in regularizing the inverse, and this is sort of a meaningless slide, but what we do is, as I mentioned, add alpha I, invert the channel, then multiplies by H, and you're getting this. And it turns out that you can analyze this and actually in closed form get a feeling for what alpha is the optimum alpha here. And it's going to be a trade-off between making the inverse well-behaved and adding interference. And you want some optimal point where we don't add too much interference, but we still make the inverse behave nicely. And so people who want to see the details, I can point you to where they are. But the idea is that an alpha can be found in closed form for this scenario. And the resulting capacity I can plot here. So again, the blue curve is the sum capacity that we're trying to achieve as a function of the dimension K. Again, the red curve is the plane channel inversion that's hitting its limit. But now the magenta curve here shows that just by adding alpha, and an optimum alpha, we can boost the capacity to grow linearly. Well, it's not growing at the right slope, and the gap is again increasing as a function of the dimension K. So we're not quite all the way there yet. So the vector perturbation will play a role. The goal will be to form a V from the U such that when I multiply the V by H inverse, the norm is much smaller than if I had multiplied U with that same H inverse. But of course I need the V to be decodable as U at the receivers, and the receivers don't know what I'm doing at the transmitter. So this V had better be equivalent to U in terms of data, even if it's not equivalent to U in terms of this norm. Okay? And there's an idea in Tomlinson-Harashima precoding, which people may or may not be familiar with, which originally showed up in the 1970s as a way to deal with intersymbol interference on the scalar channel, where the data from the, where it's assumed that the transmitter knows the channel, the ISI channel, and is able to compensate for its knowledge of the channel by precoding the data that it sends out, knowing of what the receiver is going to receive. In Tomlinson-Harashima precoding, the data from previous transmissions is in some manner subtracted off the data that's going to be transmitted currently to effectively at the receiver cancel out the ISI. And there's the same trick that we can use here, or a similar trick, but we're going to be using a vector form of it. We're not going to be doing it on a user-by-user channel way. We're going to instead be using it in a vector form where we add an integer offset, which is actually a vector. So with a good choice of L, we're going to steer V into the space of small eigenvalues of H inverse. So that's what the role of L is going to be. And a good choice of tau, we can still recover U at the terminals without distortion. So
there's some power adjustment using the L. tau really helps. But somehow I guess it's in your formula for like you somehow aren't cheating by using more power by using.
Well, gamma is I'm always going to transmit unit power. So the gamma will act as my normalizing constant to make sure that that happens. And the smaller I can make gamma, it's sort of the less normalization I have to do at the transmitter.
Okay, so then it just becomes you get the best gamma and then you know.
Yeah. So my transmit power is always the same. It's just that gamma will be smaller, and so I've effectively normalized less, and the receivers will see more power as a result of that. Okay. So going over quickly what adding an offset does to the original range of the constellation points is supposing I had just, and I'm looking at just a real part of a transmitted signal. Obviously everything is complex here, and I often switch between real and complex without notice, but to show everything complex is a nightmare, so I'm sticking to real things. Suppose I had a real constellation of these four original points here, and the bit mapping is given above it, 0, 0, 0, 1, 1, 1, and 1, 0. Now, if I took this original range and I added an integer offset to it and moved this entire range up to here, the receiver could still decode what I intended just by taking what it received and subtracting the integer offset off. And the important thing is it doesn't know which integer offset I've added to it, the receiver, and it doesn't need to know, because no matter which multiple I added, whether I moved it all the way up here, all the way up here, the receiver just mods it away and brings the constellation back to its origin and can decode from there. And this speaks to how we might choose tau. We want to choose tau such that the original constellation is moved far enough away so that I can't accidentally mistake this one for this symbol. There's no overlap. And the further away I have the constellations, the better. Okay. So I could choose tau really big, but on the other hand, if I choose tau very big, I won't have good control over the direction of the vector, and I want this vector to lie in the small eigenspace of H. And making tau very big, I'll start losing that directivity. And so there's going to be two offsetting roles for tau. One is move the multiples of the constellations away from each other, but the other one is, and that will suggest make tau larger, but the other one is move the vector into the small eigenspace of H inverse, and that's just make tau small.
Why did you say that the receiver doesn't need knowledge of tau? How does it grab from?
I'm sorry. How does it
bring it? How does it align it with the center without knowledge of tau?
Because the receiver, if I take the original constellation, is confined to this region right here,
okay,
and the receiver knows that. And now, if I add any integer multiple of this and move it up here, this symbol is uniquely decodable as 0, 0. Because it's just tau away. This symbol, again, is also tau away, so it's uniquely decodable as 0, 1.
Right, but what about the case when there's enough noise to confuse the receiver as to whether the tau is, say, 3 or is it 4?
Tau is fixed once and for all. It's never adjusted. It's a design parameter.
So the receiver knows tau.
The receiver knows tau, and it's a design parameter that's chosen at the very beginning and never moved, no matter what the operating conditions are. Okay, and we can make tau as big as we want to move these guys as far away as we want. And there's no power penalties. Remember, the gamma is going to be the role of the power penalty. So putting tau all the way up, no matter what integer offset I add here, there's no penalty in terms of power until I take the V that I get and multiply by H inverse and normalize. That's where I might see some penalty if I have long designs. Did you have a question?
No, that was...
Same question. So here is an example of uncoded performance. It's a 10-dimensional system transmitting 16 QAM uncoded, and you're seeing rho on the x-axis and symbol error probability on the y-axis. Before I talk about what's on the left there, the red curve represents just pure channel inversion, which we've already gone over time and time again as being bad. The dashed dotted line represents if I put in an alpha, okay, which seems to improve things, but really not all that much. Okay. The solid line represents what if I didn't use alpha but only tau. The dashed blue line represents a combination of both alpha and tau effects, which is the best. The dotted line, which I didn't go into at all, is a QR-based technique that uses a V-blast type of ordering to the columns and does a sequential precoding modulo type tricks along a triangular matrix. And if people want to know the details of this particular technique, I can give you. But a lot of people have asked me about this, people who happen to know this area, and ask me how it compares. So I throw it in there just to show that it's not quite as good as doing the joint optimization, which represents these curves here. Now, on the left here, I mentioned sphere encoder, so we need some algorithm to do this minimization. As you can imagine, it's a non-trivial minimization. The L prime here, I want L to be the argmin of this. L prime is allowed to range over all possible integers, real and imaginary parts. You can imagine how a search is not going to be, exhaustive search is not going to be the way to go. So you need something more clever than that. And again, what we're transmitting in the end is this quantity here, okay, just to put it all in one place. Any more questions about this?
I'm sorry, what does the solid blue line represent?
This represents when you don't use alpha, don't use this here, just the dashed line represents using both alpha and the tau. So here again is the coded performance, which same curve I showed you some slides ago. And the point being that there's a lot of good reasons to understand gamma, because it's gamma that's determining this gap here for us. So some more tantalizing properties of gamma. So now I'm going back to that integer problem. U is plus or minus 1, and I'm allowing multiples of 4 to be added to it. And I'm looking at V as being the resulting vector I get. So choose U randomly, minimize that norm, so choose L and get V. And then looking at the inner product between the eigenvectors of H inverse and the V, and to see how it behaves here on this graph. So what do we see here? The green curve is the easiest to understand. It shows the eigenvalues of H inverse in ascending order. And you see there's some nice small eigenvalues in H inverse, but there's some very nice unsmall values on this side here. And in fact, the largest one, I think in this particular case, the average is around 350. So we want V to point away from the eigenvectors associated with that eigenvalue. And you're getting that in a sense, because the blue curve represents the inner product between the V and the eigenvectors. And you're seeing that the inner product is they try to make the minimization seems to try to make the inner product as small as possible when the eigenvalue is large, and as large as possible when the eigenvalue is small. And this goes off a pretty high value there too. And the red curve represents the weighted contribution of each eigenvalue. And this, I think, is particularly tantalizing, that somehow the product of the eigenvalue times the inner product is being made roughly constant. And this is something, I think there's something deep in there, but I'm not sure what it is. The vector V seems to align itself in an equal weighted fashion with all the eigenvalues. And we'd like to know why that is. See, if V were unconstrained, if I didn't have these constraints of all these junky integers, then I would take V and line it up directly with the smallest eigenvalue of H inverse. And so you'd see no contribution from any of the higher ones, you'd just be lined up with the smallest eigenvalue. But that's not the case here. It's because of the integer constraint that we can't do that in general. And instead it seems to elect to give an equal weighting. So again, V is aligned more closely to eigenvalues corresponding to small eigenvalues, and all eigenvalues seem to contribute approximately the same to gamma. Why do I have 10 here? I have no idea. This should be 22. This is a 22-dimensional, oh, I know. My earlier simulations, I did a 10-dimensional one, but I got a faster computer, so I can go up to 22 dimensions. So, okay, maybe the original problem is a little hard, but maybe there's some easier versions of it that would be also equally interesting. This is sort of more or less the original problem. Suppose we just stick to reals instead of complexes. Would that be easier? Okay, how about letting U be just chosen uniformly rather than plus or minus 1? Is that going to be any easier? Because I've gotten rid of these multiples in other businesses. How about omitting U altogether and just looking at the odd integers, L? Does anyone have anything any ideas along those lines? These are all different gammas, but they, I think, have something to say about one another. So where to go from here? The original integer problem, are there any techniques that we should be looking at? People have suggested Fourier techniques to me without being very much more specific. I open up a Fourier book and I say, well, I can read about Fourier series and Fourier transforms and Fourier integrals, but not getting much further. Matrix theory, well, I can open up a matrix theory book and discuss random eigenvalues, and you've seen some of that. But the combination of random eigenvalues and integer arithmetic seems to be elusive right now. That's the math problem. How about the communication problem? Well, as I showed you in this particular case, everyone had roughly an equal channel, at least statistically. Everyone was given the same H. Not the same H, but statistically the same H. So in practice, of course, there'll be users who are near and users who are far. And this algorithm has to be modified accordingly. There's certainly a lot of scheduling issues. I mean, I've been looking at just the same number of users as I have antennas, but suppose, as is more practical, you had 40 users and just 4 antennas. How would you schedule the users 4 at a time, say, to service, which is really what you would try to do in this trick. There's a whole scheduling problem there. The integer precoding part, which I glossed over as a sphere encoding problem, is rather complex, especially for very large dimensions. There's lots of good tricks for making that easy, though. And the notion of getting channel information at the transmitter, which is needed to make this whole thing work, that is somewhat open, but we have some work on that addresses that problem too. It turns out that the antennas can actually help you get the channel information back at the transmitter. So antennas hurt you because of the channel information you need, but they help you to get the information back. So they seem to offset one another. And for people who are interested, there's a whole paper there.
So on your previous slide, it seemed like some of the problems, like you spoke about, U is random.
Yeah.
But are you going to sort of solve it for each U, or like what difference does it make if you're choosing a random U if you're not? Are you going to take an expected value over?
Right. Yeah, I think that would be the only meaningful statement to make, an expected value.
And
So,
that sphere encoding problem, is that like a problem you solve once for each channel H, or do you solve it for every, like can you solve it once beforehand? Like it's not a design problem, you solve it for...
No, as new data comes in, you need to solve it before sending it. So, yeah. So
like every instantation of the channel, you have to pre-code for that channel.
Right, but even if the channel is...
Or U.
Of U. Yeah, even though the channel's fixed. But see, that there's been a significant inroad into that. There's an algorithm called the LLL algorithm, which is an integer minimum norm solution vector integers minimum norm solver. And this algorithm can be done once for the channel that you're given, and then very quickly for each U you can find the minimum norm offset to add to it. And so that particular, we don't use that algorithm, but I saw somebody else who proposed it for this problem. It seems to be very handy for this problem. So the complexity of the algorithm is with the channel rather than the U in that case. In my case, it's with the U.
Okay, so you don't explicitly compute any eigenvalues, so you don't need to assume any statistics or anything?
No.
Okay.
We just evaluated it for the particular H that the Rayleigh H. But you could do it for other H's as well.
Do you have any results for the non-square case?
Non-square means more antennas than users?
Yeah, M is not equal to K.
Yeah, there are a lot of people who have looked at that.
There is a possibility that the matrix might be well conditioned. In
Right.
that case.
Right, but then you'll still be far from, my contention is you'll still be far from capacity, because if you had more antennas than users, why aren't you servicing more users to fill out the degrees of freedom that you have? So I think you'll always gravitate towards the square case, provided there's enough users, of course. But usually the number of users is not the bottleneck, it's the number of antennas. So you always look at the square case, I think. It's the most interesting case.
So when K is greater than M,
Mm-hmm.
why did you say that you might want to just schedule and do like it's still N by N?
Well, because in terms of the total throughput you're going to get to a large number of users, you're not going to do much better than servicing them M at a time in some kind of a sequential fashion or CDMA-like fashion. If you try to service many more users than you had antennas, you don't have the degrees of freedom available to you to establish separate channels anyway. There'll be interfering channels. And in a case where you had servicing only M antennas, you see I'm setting up separate channels to every user.
Right, so but if you were doing some kind of CDMA signature spreading or something, right? Is it clear why you could not have some? You're right, probably, you know, you could still, I can see why you might do a little better than M by M. If you were able to sort of separate out interference by using something else.
Yeah.
It's possible, isn't it?
I think so, but yeah. It won't be this linear type of every year.
Sure, sure.
We had an observation that when the matrix slightly deviates from the square case, the condition number becomes very good.
Mm-hmm.
So is that a trade-off between your...
What does slightly to you mean? Like, if it's M by M minus 1, say, or something, if M is small, that's still not, that might be very good, but as M gets large, it's almost like square again, anyway. And so, you can still benefit. I mean, you can, so there might be a right trade-off. I mean, you can still do the, this, even if you have a non-square H, you can, of course, you can still do these same tricks, regularize and add an integer offset to fix it if the norm is bad. But I agree that maybe by taking one user away, you might get some gain there. But you're losing, your capacity is going to get hit by as many users as you eliminate.
So, did you ever compare this with, I guess dirty paper just gives you the upper bounds and the capacity. So is there any practical way of implementing that?
Not that I know. Certainly not in this vector case. This is a 10-dimensional problem. Not even in the scalar case do I know of a effective dirty paper problem.
Well, Uri, your Technion, last I heard was at MIT working with David Horn. Uri, why do you have practical techniques?
Does anybody else think besides Uri that he has a practical technique? I saw a very elaborate flowchart that he
we
gave.
did, but the gains, at least for the problems that were evaluated at the time, weren't great enough that we looked at anything appropriate. But he did spend some there and worked with Stephen.
Right.
He seemed to be legitimately onto something.
Okay.
He did his doctoral dissertation on the subject and reported things coming in.
Well, you would have to multiply that by 10 effectively to get a 10-dimensional version, I guess.
So you were sort of saying roughly, and you were sort of conjecturing that you were about 4 dB away from the operating point of 10 dB or 11.1, whatever. So how much are you away if you go to if you make the sigma square even smaller, whatever? Suppose the operating point was 20 dB. If your noise, effectively your normalization is hurting your signal power relative to the noise power.
Right.
So how much away are you if you go to say 20 dB?
I think it's fixed at roughly 4. If I recall, even when I went to lower SNRs, it was roughly that. And when I went, I didn't check much higher because the data rates were pretty big at that. But the reason for it is this gamma, and if you look at what the expected gamma is just on a simulated basis, you can calculate, if you believe the simulated gamma is roughly what you'd expect to get on any given run, you can calculate how much that gamma is hurting you. And it's not quite 4 dB. See, there's many tricks that I really haven't covered on how to actually shrink that gap a bit. Where is it? So the modding of tau is damaging you because, as other people suggested, you might be wrapping noise over from upper points onto yourself. One way you can avoid modding tau is that you can use knowledge that most of the time, in fact, I'm not adding an integer offset to the data. 80% of the time I'm not. That's what that one curve showed you. 20% of them are getting integer offsets, 80% are not. So the PDF at the receiver that does the decoding can say, hey, most of the time I expect no integer offset, and so I add a 80% weighting to the fact that I'm receiving this without integer offset, but then I add 20% weightings to, and then it turns out that you add only 1 or 2 integer offsets. You never add more than that. So you can easily put a PDF at the receiver that incorporates that knowledge and never do the modding. And so you gain half dB by doing that, I found. But I think the remaining gap to capacity may be a function of whatever the gamma is. And I'm not sure. I even didn't discuss how to choose tau. Remember I said there's 2 competing rules for choosing tau. Choosing tau big makes the constellation replication far from one another, but doesn't allow me to steer the vector very, very carefully. I don't know what the right trade-off for that is. So there's lots of places to push on this to try to shrink the gap, and I don't know where the best place to push it.
You didn't jointly optimize.
No. One other thing that I didn't cover and nobody caught me on, or if they did, they're not saying anything, is this choice of alpha, which I can actually find in closed form when I don't use the tau. I don't know how to find the right alpha when I do use the tau. It turns out that a much smaller value of alpha is needed there. That was a numerical sort of optimization there. Understanding what the right amount of loading should be to get a little bit of a gain there is not clear at all, because this integer optimization is so poorly understood. Any more questions?
Okay, we should thank.
Yes, thank you.